Video number 1 of our next chapter, chapter B as I'm calling it. And we aren't going to start with basically a section in chapter 2. I'm mixing things up here. So it's not a typo that this is section 8.1. This really is in chapter 8, where I'm just going to take this one section from chapter 8 and combine it with some other sections in some other chapters. Okay, so don't freak out here. But we're going to talk about something that hopefully you have talked about before, the Pythagorean Theorem. We're just going to make sure that you remember what it is, how it works, and we will apply the Pythagorean Theorem tomorrow during class. Now, the Pythagorean Theorem, it only works in right triangles, or it's only true in right triangles. So if a triangle is a right triangle, and how do we know if a triangle is a right triangle? Well, it needs to have a right angle. So we absolutely need to see that little 90-degree angle box there. So if we have a right triangle with a right angle in it, then a squared plus b squared equals c squared. Now, does it matter which sides are a, b, and c? Yes and no. The c is absolutely the most important side to identify. The other two sides, the a and the b, really don't matter if you mix them up. So a and b represent what we're going to call the legs. Okay, they are the legs. Let me click that. There we go. Let's change the color up. Come on, work with me here. Work with me here. So a and b represent the legs of the right triangle, which are adjacent to the right angle. Okay, so here's a and b, here's the right angle, and adjacent, remember, means they're just right next to, they're connected with. So a and b, they're the two legs, and it doesn't matter which one's a and which one's b. Okay, you can mix them up. Truly doesn't matter. The c side is the hypotenuse. And it's always the longest side of the triangle. And it's always opposite of the right angle. Okay, and what do I mean by opposite? I mean it's literally on the other side of the right angle. Okay, the hypotenuse does not touch, it is not adjacent to the right angle like A and B are. Okay, so it's absolutely important that we be able to identify which side's the hypotenuse and the other two sides are the legs. And again, it doesn't matter about which one's which. All right, so let's apply the Pythagorean theorem here. We have a right triangle, so we may use the Pythagorean theorem. Now, again, the first thing I would do is identify the c side. Which one's the hypotenuse? Well, it's the one side opposite the 90-degree angle, the one that doesn't touch it. So here's our c side, which means the other two sides, doesn't matter which one we call a or b. Typically, I call my variable the a if I have a choice between a and b. So if I write out the Pythagorean theorem, a squared plus b squared equals c squared, and now I'm just going to substitute in. So this isn't entirely necessary. You could start with the first thing I'm about to write here. So a is my x, so it'd be x squared, plus the b is what I call 5, so 5 squared equals the c was my 16, 16 squared. Now, the next thing I'm going to do is just a little bit of simplifying. I can't do anything with x squared, but I know 5 squared is 25, and 16 squared is 256. Now I need to work on getting that x squared all by itself. So I'm going to move the 25 over, and so I get that x squared is equal to 231. Now, to get rid of the square, the last thing I would have to do is square root both sides. And here's where, from the previous chapter, simplifying square roots is going to definitely be seen. Now, can I break down the square root of 231? I don't know. Let's test some things out here. Obviously, no even number is going to go into 231 since it's an odd value. So I might try to think of 3. And if I add together, if I remember my little divisibility rule for 3's, if I add the individual numbers, is that number divisible by 3? And so 2 plus 3 plus 1 is 6, and 6 is divisible by 3. So I know 3 will go into 231. The question, though, is now how many times? And so what would I get? 3 would go into 23 7 times with 2 as a remainder, so 21. So it'd be 77. And then with 77, we could do 7 and 11. But then that's as far as I can go with the 3, the 7, the 11. And do I have any pairs to work with? No, I don't. Which means the square root of 231 is as simplified as it can get. So that would be my answer for x. Now, the square root of 231 is, what, 15 point something, 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 infinitely many decimal points? Should I write that? No, I want the exact answer as a fully simplified square root number. So the square root of 231 is the answer I want to see. Number 2, At first glance, you look at this and you go, oh man, there's square roots now as part of sides. This is going to be even tougher. But it's really not. Let's kind of walk through this and you'll see how much easier really this problem is. Now, we've got a right triangle, check. We can use Pythagorean Theorem. So a squared plus b squared equals c squared. And let's identify first, what I would do is identify the c side. It's opposite the 90-degree angle, so the z is the c. Then it really doesn't matter which one's the a and the b. Typically, I call the smaller of the two numbers a and the bigger of the two numbers b. But again, that's me. So now let's plug in what we got here. So a is the square root of 14, and I have to square that. And b was the square root of 38, and I need to square that. And some of you are already seeing like, oh, well, now I know what's going to happen and why this is easier. And c is our z, which we need to square. Now, the square root of 14 squared, the square and the square root are just going to knock each other out, and we're left with just the 14. Same thing happens with the square root of 38 squared. We just get the 38. And 14 and 38 together make 52, which is z squared. Now, last but not least, we need to square root. So can we simplify the square root of 52? Let's see. 4 can go into 52. How many times, though? 13. And so the square root of 4 is 2. And 13 we can't do anything with. There's no perfect squares in it. So z is equal to 2 times the square root of 13. And that is our fully simplified square root answer. If you wrote the square root of 52, it's technically correct, but it's not fully simplified. Now, there is something called the converse of the Pythagorean theorem. And the converse just literally means taking a statement, typically an if-then type statement, and switching the if and then parts. Okay? So before with the Pythagorean theorem, we said that if a triangle is a right triangle, then the Pythagorean theorem works. A squared plus b squared equals c squared. We're going to take this part, the a squared plus b squared equals c squared part, and the if a triangle is a right triangle part, and we're going to switch them. Okay, the if and the then parts technically stay. So the converse says that if a squared plus b squared equals c squared, if that is in fact a true statement, then the triangle really must be a right triangle. So the Pythagorean theorem technically works forwards and backwards. Okay, so let's talk about what this would really look like here. So the question is this a right triangle? Well, let's see. We don't know. There's no right angle here, but that's what we want to test out. So if the Pythagorean theorem works out, if a squared plus b squared truly equals c squared, then we have a right triangle. Now you might ask, well, how do I know which side's which? I can't assume that this is the 90-degree side, but I mentioned earlier that the c side, the hypotenuse, is always the longest side. Okay, and which side's the longest side? The 53. So the 53 will be our guinea pig C, which means the 28 and the 45 doesn't matter which one's which. I'm going to call the smaller number the A and the bigger number out of the two potential legs here, the B. So now I need to see, is this, come on, work with me here, is this really a true statement? Well, let's see. 28 squared. Oh boy, we're getting some big numbers here. Let's break out the calculator. 28 squared. 784. 45 squared. Jeez, oh Pete. 2025. Now, I'm going to stop right there, okay? Because I'm going to go ahead and add these two. What is that end up being? And I get 2,809. Now, 53 squared. Let's plug that in. And I get 2,809. I get equal values on the left and the right sides. And if that is a true statement, which it is, then that must mean, is this a right triangle? Absolutely. I may now draw in a 90-degree angle marking there in my triangle, and we do in fact have a right triangle. Now you might ask, well, what if that's not true? What if the two values on the left and the right aren't the same? Then what type of triangle is it? Well, we have other types of triangles, like an acute triangle and an obtuse triangle. Okay, and you might think, all right, well, I know those terms, but they specifically relate to individual angles. Well, an acute triangle is where all three angles are less than 90, and an obtuse triangle is where one of the angles is bigger than 90, just one of them bigger than 90. And you might go, all right, well, how do I know which one's which? and we'll talk about that later. It's not a huge deal, but those are the types of triangles you would get if the Pythagorean theorem does not work out. Now, the last little bit here is anytime A, B, and C of the Pythagorean theorem, anytime they come out to be whole numbers, for example, like what we had here, all three, I don't need you, all three of these guys, the 28, the 45, and 53, notice they were all whole numbers. There were no decimals, no fractions, no square roots with them. This doesn't happen that often. Okay, and you might think, well, I can make up three numbers and make it work with the Pythagorean theorem. Good luck, try that out. I guarantee if you just kind of randomly come up with three numbers, the Pythagorean theorem is not going to work out with your three values. Okay, does that mean that there are a limited number of Pythagorean triples, as I call them here? No, there's infinitely many Pythagorean triples, but they start getting very, very, very large. Now, so I'm going to give you some examples of the most common Pythagorean triples you will run into in class. The smallest Pythagorean triple is a 3, 4, 5, where maybe 3 is A, 4 is B, but 5 definitely must be C. And you can just test it out real quick. Is 3 squared plus 4 squared really, in fact, equal to 5 squared? Well, we get 9, and we get 16, and 5 squared is 25. 9 plus 16 does, in fact, make 25, and so 25 equals 25. That works out. Okay, so you don't have to write that out, but that's just checking to make sure that, yes, in fact, it does work. Now, 5, 12, 13 also works out. 5 squared plus 12 squared does, in fact, equal 13 squared. What are some other ones? 8, 15, 17. 7, 24, 25. What are some other ones? There's some bigger ones. 11, 60, 61. 9, 40, 41. And there's really not a pattern that you can be like, oh, I think I figured the pattern out here. It really doesn't work that way. It's a pretty complex pattern, but there is a pattern. It's just something I would highly doubt you could just figure out in your head real quick. Now, besides these, I want to let you know that also any multiple works as well. And so what do I mean by that? I mean, if you take a 3, 4, 5 and you multiply all those numbers by 3 and you get 9, 12, and 15, 9, 12, 15 is a Pythagorean triple. It works out. 9 squared plus 12 squared is 15 squared. Okay? So you might go, why didn't you talk about 9, 12, 15? Well, because this is what I do. I call a 9, 12, 15. It's really a triple 3, 4, 5. Okay? And you'll see lots of double 3, 4, 5s. What would a double 3, 4, 5 be? 6, 8, 10. Okay, it's really just a 3, 4, 5. It's been doubled. So a double 5, 12, 13 would just be a 10, 24, 26. Okay, so any multiple of any of these absolutely works. Okay, so you might think of, oh, you didn't mention this one. Well, it might be a multiple of something. Okay, now, do you have to have these memorized? No. But the more you remember these, the more the math will come really, really quick. Okay. Now, the very last problem here, example 4, I want you guys to try on your own. And yes, this is a little bit more advanced. This is kind of two problems in one, if you will. And I want you to figure out the value of A. Now, one other thing I'd like to let you know is there's a 90-degree angle over here, so we know that this is a right triangle. But also, if this is a straight line, which we're going to assume it's a straight line because it looks like a straight line, if this side is 90 degrees, how many degrees must this angle be? Okay, it also must be 90 so that we get 90 and 90 makes 180. So you really do in fact have two right triangles here. But in the book and in all the problems, they'll only mark one side, and you just need to know the other side is also a 90. So let's see if you can figure out how to get this particular value A. And that is all, and we'll discuss that problem tomorrow in class.